Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
The Radiation Team is a radiation reliability consulting provider specializing in delivering customized, cost-effective radiation solutions for mission-critical space systems. They focus on accurate analysis, speed, efficiency, and necessary and sufficient engineering to mitigate the impacts and risks of ionizing radiation throughout the development lifecycle of space systems. And joining me today on the Ex Terra Podcast is Merek Chertkow, founder and CEO of the Radiation Team. Merek, thanks for joining me today.
Yeah, thanks for having me.
Let's start kind of at the beginning and tell me what inspired the foundation of the Radiation Team and how you got it all started.
Sure. Gosh, that's a big question without giving you my whole history.
That's okay. We've got time. It's the internet.
The short of it is I love space. It's always been a passion of mine. It's why I went to college. It excites me, right? So it's effectively my religion, which means that's kind of the motivating factor with everything we do. The second element of that is I was lucky to be trained at SpaceX. I got a job there in 2012, right after my PhD. And the reason I say that that's lucky is everyone knows SpaceX has done amazing things in the last couple of decades. Most importantly, I was trained in extreme ownership and getting things done and executing and going. And I think a lot of people kind of see SpaceX as a new modern doer in the space environment. So I love space. I learned how to execute extremely well. And then we have a niche field with all of these space companies exploding. We really don't have a large workforce in the radiation field. It's a hard thing to solve. It's something that you don't just go to school for. There's schools where people get training in this field, but it's kind of a secondary impact of their primary education, becoming a software engineer or electrical engineer. So the need was really there. And I saw that there's a lot of companies that aren't going to have access to quality radiation engineering effects. And so when I was at Blue Origin, I was having a great time there, but I saw a lot of my friends starting companies from ex-SpaceX, and I just saw a big growth. And I realized that they're not going to get the help that they need. So I left Blue Origin and started the Radiation Team. And now we're here to help anybody who needs radiation effects. The quick cartoon picture that I give is if there's 100 space companies, there's only 30 radiation engineers. And let's just assume that each company needs one radiation engineer, which isn't always true. The problem is there's even fewer great radiation engineers in our field. It's a really hard thing to learn. And so the supply of radiation engineers can't currently meet the demand. And with that hyper execution and extreme ownership that I learned from SpaceX, we can make a pretty big impact in the field. I'm not saying we can perfectly solve it, but sure, there was a need there. And so it was a need born out of a love to see progress.
What makes it such a challenging field?
It's not so much that radiation work itself is hard. It's that it's tricky. And we'll probably get into this later. I could deep dive on this forever. At the end of the day, it's reliability. It's making a system survive being in outer space. And for those that don't know, reliability is always kind of the last thing that's put on a program or the first thing that's cut. The obvious example is we're here to make a flight computer survive in outer space. But if a customer doesn't have a flight computer, or it's not designed yet, or they're going through major trades, you can't start analyzing a component or a circuit until somebody has decided what components or circuits are going to go in that system. Otherwise, you're just churning forever. So some big institutions have this problem where they say, we want to do this mission. And then they say, okay, what is the requirements? Let's go find a bunch of parts that work for that system, and then let's start designing the system. And if you do it in that kind of serial effort, it'll go really, really slow. So the challenge is allowing design engineers to start designing their systems and working on the reliability at the same time, and then hopefully converging at the right time. But if there's any change, it can cause a lot of negative work. So that's one of the challenges. The other challenge is understanding what you really need. When a customer or a program says, I want a 5-year lunar base or thing or space station or whatever that does this, you're like, well, what does 5 years mean? Does it mean you have to survive 5 years exactly and then you can fail on the next day? Or do you have 30% reliability, 50% reliability? You can tune a bunch of knobs and spend a lot of time deciding what's good enough for a system. And some customers have those lines really, really strict. like the big defense contractors, it's pretty clear what you have to go do, and there's a lot of margin. But for a lot of the small, young space startups, they're willing to take a lot more risk, but they just haven't, or they don't know how to decide what risk means in terms of insurance policies or business models or schedule or cost. So figuring out all these things and saying, when are we going to make an engineering design decision is a very tricky thing. It's much more than just radiation work. It's programmatic work. It's systems work, mission operations work. And so I can dig into a lot of those if a lot of that doesn't make sense, but it's a holistic approach in order to do necessary and sufficient engineering.
But it sounds like everything is pretty much ad hoc. I mean, it seems like every system that you work on kind of requires its own parameters.
That's true. That's definitely true. On that front, we have customers who say, how do we work with you? And we say, well, what do you need? Do you need testing? We can do turnkey testing. Do you need mission reliability? We can do that. Do you need support against, or not against, but with your customers and what they're asking for? So everybody has different needs. It's a little less that it's ad hoc, and it's more like the field is so broad. Identifying what is the best approach to take for a customer or for a mission is part of the challenge. Sometimes it's work at a circuit level. Sometimes it's at a box level, like a flight computer. Other times it's at the system level with fault tolerance or mission design. And so it's helping the customer understand what goals they have, which is mission success. And then it's understanding what's the path of least resistance and the best approach to take in order to get them what they need. And there's many knobs to turn, and there's schedule constraints and cost constraints. Some customers have both or none or one or the other. And so it's figuring out what they need best so that we can best support their needs.
Let's talk a little bit more about sort of like the nuts and bolts of your company. Tell me about the main members of your team, and then if you can boil down your core mission into a phrase, what would that be?
Yeah, that's tricky. We've been playing with, like what does the sentence actually say? And it's hard because of everything I was just talking about. It's quite broad. Mm-hmm. Necessary and sufficient engineering in the context of radiation might be kind of the approach we take. It means doing what is required without doing anything more. And that's born out of two reasons. One, commercial space needs that kind of approach. And two, our field is inundated with conservatism and margin that doesn't have to be there because we have new modern tools to solve those problems. So that's our mission statement and approach. And sorry, it's not a single sentence.
That's okay.
I could come up with, space radiation reliability for space systems or whatever. But at the end of the day, it's providing an optimized service.
That's when you went to business school and got all those fancy phrases, right?
Yeah, that's right. Yeah, we probably need a good one on our website. In terms of the team, it's a small group of engineers. For anyone who plays Dungeons and Dragons, it's kind of the concept of multi-classing, right? So we have a great software engineer who understands radiation. We have a great hardware engineer who understands radiation, an analysis engineer like a physicist or a statistician or a database guy. And we teach them all radiation because that's the context for doing the work. But ideally, that's the best way to have radiation engineers is take a great engineer and then multi-class them so that they know how to approach radiation effects. And in that way, I think it helps us be very holistic. So yeah, that's the answer.
Did a lot of your team members come out of other space companies, or did you get them out of college, groom them from the ground up? Kind of what was that genesis?
So we've been around for a year and a half. Okay. So I started this in late 2022. So the answer is no, we haven't raised anybody out of college yet, although we're open as we grow. All the people in this company are people who have had a good experience within the past. So we know they're really high quality people. We can set the bar extremely high. They're ex-SpaceXers, ex-Blue Origin, and then Raytheon and a couple of other companies. And we have some support from outside, like we have a project manager who has worked in the defense side before. So he really understands how the government works, which is very helpful because me coming out of commercial private space, we can only speak that language so well, but of course we want to help anybody who needs help, which includes small startups and more of the defense industrial base.
Talk a little bit, if you would, Merek, about the range of radiation solutions and services that your company provides.
Sure, that's a big one. So it's kind of twofold. There is the systems that we work on. Those can be electronic piece parts, like ICs, FPGAs, FETs, and so on and so forth. A lot of radiation companies can just test those for customers, and they can say, these are good for your system or not. So a lot of it's just testing at the component level. But then there's the box level, like a flight computer or network switch or power system. We can also qualify those higher level systems. We call those units or boxes. And then there's the architecture level, like how does this entire thing work together, and what type of fault detection, isolation, recovery schemes does it have in order to work as a mission? So there's 3 major engineering levels that we can work on, but then every customer is at a different stage of development. Some customers are at the design and concept phase. Others are at like the prototyping concept phase. Others are in the middle of their qualification and getting all their hardware from vendors. And then other customers might be launching or are looking to get into production phase. So that's kind of a large 2D matrix. And wherever they're at, wherever they need help, is where we can supply our resources. Some customers need help getting through CDR. Others need design solutions. We had one customer who was actually flying, and they had some anomalies in flight, and so they needed help with the redesign. So at the end of the day, we can provide a lot of options for a customer and say, I don't know. Okay, so one of my favorite examples is if you have a launch vehicle, if you have an engine controller and a payload controller. Right. They're not only at very different ends of the rocket in theory, but they're used at very different times in the missions. So they have different lifetimes, and they're used in different environments. And so they should have different radiation requirements. But if the engine controller has a problem in the box, let's pretend that it's kind of a state machine, right? The solutions to that problem could be swapping out the component if there's availability. It could be changing the software if that's an option within the box. It could be, if it's a dose problem, it could be adding more shielding to the box. So that's a mechanical problem. And we could also move that box in the system where it's at, so it also gets more shielding. So that's another mechanical problem. It could be changing the mission operations and the timing of when the engine controller is used. So if you use it just outside the Van Allen belts or just beyond the Van Allen belts, that can statistically help the claim that it's reliable enough. And so, mission, program, electrical, mechanical, these are all things that we can work on, but a customer doesn't know those trade spaces. So we say, here's all your options. And only the customer knows their business model best. And maybe it's cheaper for them to have a software solution than an electrical solution. We don't know that. So we try helping them understand what the options are, what it would cost, what the risks are associated with it, and then work with them to get to where they need to be. Or they can just accept the risk. Understanding what the risk is too is part of it, saying this is your risk. And you can accept this because you're your own customer and you're brand new and you're the only one who cares what this mission means to you.
To the layman, we think about radiation protection as being the foil that was around the limb on the lunar mission. But it's really the things that you're talking about are far, far more involved than just preventing radiation from getting through to the components. Yeah,
that's right. Sometimes customers will come to us and ask for help, and they say, we want more shielding. And that's often the worst ROI solution, just adding more radiation shielding or analyzing it. At the end of the day, it is about understanding the environment, the natural environment on the outside, just free floating in space, and what it means for that environment to get down inside to where your sensitive volume is of the device or the thing that you care about, that you know is susceptible, or you don't know it's susceptible, and you have to go test it to say, how susceptible is it? So I know where it's at, and I know the stress that's going to be applied to it, and is that a problem? It may or may not be. It could have large consequential effects on the mission as a whole, or it could have no consequential effects, in which case the answer is don't do anything about it. So sorry, I don't remember your question, but yeah, it's a lot more than just saying, what does the environment look like? It's the consequences of all of that, all the way up the chain.
You answered the question, trust me.
Okay, yeah.
So then, Merek, how does your team approach the conceptual design and product definition stages for new products?
Good question. So when you say new products, I'm going to take that more to mean new customers who have products, because sometimes the products are pre-existing.
Should have said new projects, probably. But
yeah. So at the beginning, if it's a new project, one of the first things we ask customers are, what are your requirements and can they be changed? Not can we change them, because we don't assume that they're wrong. But if they're not modifiable, then we know what we're working in. Okay. Historically, our field, like I said earlier, has a lot of conservatism in it and very large error bars. And before we go do a bunch of testing and spend a great deal of resources setting up a program to go do all this engineering work, if we can make the problem go away, then great, work's done, and we've provided the best value to our customers. As a little example, again, launch vehicles, because they're quite dynamic. If someone has a large TID program, total ionizing dose requirement, that they have to go do on a launch vehicle, our first thing would be to say, well, let us do the environment analysis and show you don't need a dose program and not do any dose testing. And you're done. It's kind of a peeling the onion or back of the envelope type approach. So we find out what the critical work is that needs to be done. And then we work with the customer to help them understand what it's going to take to get there to meet the goals. So that's how we kind of take the first approach to new products. An important part of that too is having a good enough relationship to say, can we call your baby ugly? Do you want us actually doing strategy consultant and real advising? It's kind of like a dating advisor, right? It's you need to change your wardrobe, and we need to fix your hair, and you need to do these things differently because this is what hasn't been working in the past. So some people just want turnkey support. They want to throw work over, have us do it, and send it back without asking, why are we doing this, or what are your requirements? We like to work in the space where we really are acting on behalf of the customer to say, this is what you should be doing because we understand your goals. We know what it takes to get there. Some customers want to have that kind of deep embedded relationship and others don't. And that's fine because we want to, at the end of the day, provide them with whatever they want. So we ask them, do you want us calling your baby ugly? And a lot of them say, yeah, tell me what I'm doing that's dumb or that I shouldn't be doing. And we support them in that way.
My guest is Merek Chertkow, founder and CEO of the radiation team on the Ex Terra Podcast. Take a moment right now to click subscribe to be sure you don't miss any of our podcasts, or if you're watching on YouTube, any of the videos from Ex Terra, the Journal of Space Commerce. Merek, without giving away any company secrets, take me kind of through that testing process. How do you test for radiation in space without being in space?
Yeah, good question. These are all good questions, by the way, so I maybe won't preface that again. But that is a good
well,
question.
Thank you.
There's a lot to that I want to talk about, which comes down to like, how do you know what you're testing on the ground is right to be representative of space? We can get into that if you want, but at the end of the day, there's two primary types of testing. There's single event effects testing and then dose testing, and there's other subcategories. But it comes down to knowing what type of random stochastic processes you're going to see in space against radiation effects. That's SEE testing, single event effect. And then the other one is dose, which is more of a long-term degradation. And it can happen on electronic systems or materials like glass darkening and so on and so forth. So my community uses facilities that we rent. There's heavy ion facilities, which we use to test for galactic cosmic rays. Basically, when stars explode and they go supernova, they scatter all the periodic table of elements throughout the universe. And so there's actually like these charged ballistic missiles that are just flying everywhere in the background. They're well shielded from Earth's magnetic shield, or at least they're bent and funneled up towards the poles. But we need to test against those environments, and we do that at heavy ion facilities. These are hundreds of millions of dollars. These facilities cost to build. So nobody has their own. We rent them from national labs, and there's about 4 of them in the United States that are quite common. So everyone in my field is struggling to go get that time. And at the end of the day, it's pretty simple. You take a piece of electronic hardware, ideally like an IC or FET or some type of smaller component. And for those that don't know, basically, it's the thing that looks like a cityscape on your motherboard on your PC. So it's all the components in electronic systems. We bias them, we power them, we put them in a functional state that is hopefully representative of flight, and there might be multiple states. And then you set them up and you hook up a data acquisition system and power and whatever else you need, and you basically turn them on. And then you request the beam, and there's a bunch of different ions and species that you can choose to hit it with, and you choose those carefully so that they represent what you're trying to do in space. The longer you are in space, the more likely you are to see a rare particle that you otherwise wouldn't see. And so you choose the beam and then you expose it and you watch what happens. And you're either watching for a non-destructive event like a bit flip in a memory of 1 to a 0, or a destructive event or a transient if it's an analog device, and you see how this device responds. Depending on the technology of the device, which I won't go into, but all different devices are made of different materials and have different structures. You can expect them to have different responses, and you can sometimes expect them to break or not break, or have what we call a latch up, or have a functional interrupt where they stop working and they can come back with a power cycle. So we kind of go in with a high level plan on what to expect. We take our data and then we're done. And but a test can usually easily take a full day. Sometimes it can take multiple days of testing to test a range of parts. And then you collect your data and you write reports and you go back and you say, all right, here's how this device responds. And for your mission, you can either expect it to have a destructive effect or not, or here's the effects that it does have. And you can either use a different part if that's not acceptable, or at the circuit level, you can do a design that mitigates that problem so that the customer can use it, or they can just accept the risk. And so it's about a feedback loop of saying, all right, customer, what are you trying to build? What is that system composed of? We break it down, we test those things, we see how they respond, and we feedback and say, this does or doesn't work in the system. And you just kind of repeat that cycle. So it's kind of like walking and looking under a bunch of rocks. And if everything breaks, then you got to go back and redesign everything. And so the implied thing here is you want to do what's highest priority for a system. If it has a core piece of technology that everything else is built around, you want to test that thing, because if that thing's not good, everything else has to change. As opposed to some very common piece of electronic, if that fails, even if it's critical, there's maybe 10 or 50 other components that you could choose from and swap that in. So testing isn't just as blind as saying, oh, well, let's just test this stuff. You have to test it in context for how you're going to converge towards a good solution in your system. I'll stop ranting if that ended up being a rant, but that's hopefully a good answer. And that was just SEE. I didn't even cover dose. Sorry, I totally forgot about dose, but we can move on or keep talking about that if you want.
Well, we can talk about dose, but I also want to kind of get into the difference between testing hardware and testing software, because you mentioned something interesting about flipping a 1 to a 0 and how that could certainly affect whatever the program is. So is there a different way that you test software, and how would someone then have to go about rewriting software to make sure that doesn't happen?
No, it's pretty much the exact same. When you test a piece of hardware which has software on it, and so maybe I won't make assumptions here. Yes, testing software is a concept, but at the end of the day, that software is on a piece of hardware. And when you test, you're testing to see if that hardware keeps the software in the way that you would expect it. So if you take like a memory, it has information on it, and if that information becomes corrupt, the question is, can the software fix that problem in flight or not? And can you bake in a solution? Or if you have a system on a chip, which is another way of saying a fancy processor with lots of other peripherals, is it going to keep its state, and is it going to keep functioning in the way that you expect it to, because its software is being negatively affected? And so just like I described how we test hardware, we do the same thing with software. We're just understanding the state that it's in, and you might be driving modes. If it's reading or writing or trying to do things, we just continue to monitor the hardware and the software and see how they function. The goal here, of course, is to say this is software that's in flight. Don't want to go down this road? Sure. So if you have a very complicated system, you really only care you could fully qualify the system as it's designed. So like an NVIDIA GPU, right? Mm-hmm. We could test that for NVIDIA conceptually in all the ways that it could be used, or we could test it for a customer in only the limited ways that they're using it, with limited software and functionality around it. So it depends on who's interested in what parameters and capabilities this thing has. We can test with those in consideration.
Is there a difference, or does it make a difference that you are testing in an environment with an atmosphere as opposed to in the vacuum that's in space?
So only if it affects your test setup. And the answer is yes, it can do that. So in space, the particles that are flying around are extremely energetic. They can get up to conceptually infinity, right? Up into the giga electron volts and above. Giga is not that, nowhere near infinity, of course, but it's much higher than what we normally test on the ground. So on the ground, we test with much lower energy particles, which means they're only representative of space. And some of the test facilities, the particles are so slow that you do have to account for the atmosphere that we're in space. So it's really not that big of a problem. It's more of a test logistics issue. But conceptually, from the physics perspective, no, it doesn't matter. These very small, atoms, basically stripped atoms, so they're ions, are impacting a sensitive device like an IC. It really doesn't matter that there's atmosphere out there because it's not affecting the functionality of the device. So it's purely a test logistics issue problem.
Let's talk about the dose issue for just a moment, because you mentioned that, and I'd like to dig into it a little bit. And obviously, that's how much radiation something can stand. So talk about testing in that parameter.
Yeah, so that's a little bit easier because the dose facilities, normally you test with like cobalt-60. They're much easier to rent. They're more accessible. So lots of people have their own sources. And it's effectively the exact same thing. You take the hardware, you put it near a dose source, and you monitor how much dose it's getting, or you calculate how much dose it's going to get in its exposure to time. And then you see how the component degrades. So unlike an instantaneous destructive event that can happen kind of randomly depending on how it hits the device, and rather than a bit flip, the electrical parameters of a device begin to shift and decay and decay and decay until the device gets into a state or an area where it stops working against its data sheet, or it just stops working completely, and then the device is no longer useful. So dose is much more straightforward, and given that it happens at the end of missions when people design against, it's more of a degradation problem that you have to watch over time. And the goal, of course, is to have the device always working well past the end of the mission, in which case you're safe. So dose is an easier line to draw when it comes to reliability calculations, because when a mission is flying, everything's going to get the same dose, roughly. Things have different material types and different shielding, but for the most part, dose is a much more straightforward problem than single event effects.
Just a couple of things more, Merek, and it's going to be kind of time to look into the crystal ball, both short-term and long-term. Yeah. Talk to me about the advancements in radiation technology we can expect to see in the near term.
Advancements in radiation technology. That could go several ways. So the way that I think about it is there's a lot more space systems, programs, companies doing things in space. Right before, it used to just be like nation states could only put stuff in space, and now you can have two young guys start a new company and seriously talk about doing something really cool in space with their own design space system that maybe is backed by venture capitalism. So there's hundreds of space companies now. And this is because the launch services are much cheaper, and because people can launch things cheaper, they can launch cheaper systems and fly them again. So instead of having 5-year or 10-year satellites and everything costs like James Webb or Hubble, you have smaller satellites that are faster, cheaper, which means people can take more risks. You can do the iterative design process faster. And what this means is people are going towards commercial electronics rather than space-grade electronics. And so I think that radiation is going to become more normalized. Just basically risk is becoming more acceptable. And that means we're going to have more exposure to it. We're going to understand it better. The thing that we haven't talked about yet is my field, or the radiation field. It's both a combination of engineering that needs to happen, but there's a lot of research that is still ongoing that we don't have great answers to yet. And even some of our methodologies, it's like, well, this is the best way we know how to do things. The way we provide the metric on the energy that we deposit for heavy ion testing, linear energy transfer, for example, that's not perfect. We all know it's flawed, but there's active research in that area. There's also active research in what is the space environment really like? What does it contain? There's papers that come out every year like, actually, this is a better model for the environment, or this is a consideration people haven't thought of. So I think that the research component of our field is going to be supported by and driven by just actual experience in space. Like SpaceX put out a paper saying, hey, here's what we observed on our Starlink system. And that tells us a lot about the environment that, maybe a NOAA a satellite or some research satellite that went up there with instruments to actually measure the environment intentionally could answer. But in this case, people are just going to have experiences. And as we have more experiences in space with radiation effects, we'll say like, hey, everyone expected this to happen, because the only way you can really know about the environment is going and measuring it, and having exposure to it.
Right.
And so the more exposure we have, the more we'll understand it. And then the more we can have that be a feedback loop on what we're doing in space. There's also the CHIPS Act, right? I don't know if everyone knows about the CHIPS Act, but it's basically billions of dollars, hundreds of billions of dollars for research and development for the U.S. Semiconductor industry. And as new technologies come out and new node structures and 3D devices and FinFETs and all these other neat, interesting ways of creating electronic systems, they're going to have new responses to radiation. And so research is going to be necessary for that to work. But some of these components are going to be great for space and others aren't going to be great for space. And so it's just kind of a growing ecosystem, I think. And there's parts of it that are going to go away that historically we didn't have good answers to that we will. And there's going to be new problems that come about because of new technologies and other things that we experience and new types of missions to develop. So was that an answer to your question?
It was, but now I have a follow-up question, and that's to look at, and we ask this question of all of our guests, and that's to look at the next 10 to 15 years in space commerce and the role of your team in it, and tell me what you see.
Yeah. Well, so the reason we started this company, as we discussed, is because there's a lot of people that need help. And even if they all want it and are willing to pay for it and appreciate that radiation is a risk and say, yes, I need to address this, so what do I got to do to address it? Right now, I don't think that they can get the support that they need if everybody said, let's do radiation. And so that's the role that we're trying to play, is lowering that barrier for everybody who needs it. There's other companies out there that are working on this problem as well in a variety of different ways, but it's less how can I create a successful company that grows and is large so that we can make money and just be a business. It's not about that. It's how can we make a critical impact to the space industry for anyone who wants to go do cool stuff. I want to see lots of space stations and lunar programs and Mars missions and LEO satellites and geo satellites. And, this is on those companies to decide what interesting programs we need out there. And I want to make it so that there are radiation problems that exist today, and there are people with jobs in radiation fields that exist today. And if those can go away because those problems can be solved and they're no longer issues, great. Like, that's what I want. I would love to make radiation not be a problem. If I could design myself out of the job and say there is no more radiation problem, great. That's one more reason we can easily access space and go do amazing things. And I'll go get another job, right? Really, I'd love to be an alien biologist if we can get there. So it's less about job security, job program, and it's more about progress for humanity in the U.S. to go do cool things. So we're looking at ways to make that as real as possible and getting out of our own way and helping radiation stay out of the way of other companies so that they can focus on their core technologies and do the things that they want to do. And so the answer to your question is I have some ideas, and I'm not going to fully expose all of our plans. But the goal is to make radiation as little of a problem as possible for companies who want to go do stuff in space.
And it sounds to me, at the end of the day, you're the kind of a guy who, if they didn't have that job you wanted, you go out and create it.
Yeah, hopefully that's the case.
Merek, we are out of time. Thank you so much for joining me on the Ex Terra Podcast.
Yeah, thanks for your time. I really appreciate it.
Merek Chertkow is the founder and CEO of the Radiation Team. And that's going to do it for this edition of the Ex Terra Podcast. You can subscribe to the audio version of the podcast on Spotify, Apple Podcasts, Google Podcasts, Audible, and many other popular podcasting platforms. Be sure to click subscribe so you don't miss any of our podcasts or any of our other videos. You can also get daily updates on space commerce by subscribing to the Journal of Space Commerce on Substack at www.xterrajsc.com. And one thing more, be sure to connect with us on LinkedIn and follow us on X at xterrajsc. Until next time, I'm Tom Patton. Thanks for joining us.
I wanna go faster, faster. Hands in the air, we're gonna crash. Searching for the answers. My Galileo, the through is looking glass. Thirst for reason. Our dreamer's eyes we gaze into a sense of purpose, know my view. Like finding water on the moon.